In this video, I'll give you a few more details about how matrix inverses are calculated. Using a matrix inverse to solve a system of equations is relatively easy to explain from a mathematical standpoint, but calculating an inverse is difficult from a practical standpoint. After I talk about inverting matrices, I'll show an alternate technique for solving systems of equations which doesn't require calculation of a matrix inverse. Calculation of a matrix inverse relies heavily on calculation of its determinant. Determinants are indicated by placing the elements of the matrix within vertical bars. If A is a 2 by 2 matrix with these elements, its determinant is the product of the diagonal elements minus the product of the off-diagonal elements. So the determinant of A is A11 times A22 minus A21 times A12. I'll use the determinant of a 2 by 2 matrix to calculate determinants of higher dimension matrices. It's easiest to see the process of calculating a 3 by 3 determinant by watching an example. First, choose an arbitrary row or column to work your way through. I'm going to work through the first row of this array. Take each element in that row or column, so A11, and multiply that by that element's cofactor. A cofactor is created by eliminating the row and column of the element that you're working with and taking the determinant of the remaining elements. The next contribution is going to be a negative A12. These signs alternate here. So A12, its cofactor is A21, A23, A31, and A33. Then plus A13 and its cofactor. This can be compactly written this way, where C sub ij is the cofactor of the ith and jth element of the matrix. The process is the same for a 4 by 4 matrix. In this example, I'm still working through the first row to create the determinant. The determinant is A11 times its cofactor minus A12 times its cofactor, and so on. Each of these cofactors is then calculated using the approach for a 3 by 3 determinant. The important point here is that the number of calculations required to calculate determinants and cofactors increases drastically as the matrices get larger. For a 4 by 4 matrix, you calculate 4 3 by 3 determinants, and each of those determinants requires you to calculate 3 2 by 2 determinants. Calculating the determinant of large matrices can require a huge number of operations and is really inefficient. Another drawback to this approach is that you may end up working with large numbers due to the amount of multiplications required. Using what we know about calculating determinants, let's talk about calculating a matrix inverse. The inverse is based on a matrix of the cofactors of the original matrix. Transpose that matrix of cofactors and then divide that matrix by the determinant of the original matrix. This is pretty difficult to do since it's common to deal with matrices that have hundreds of rows and columns. This means we have to do a lot of operations and we may need to divide by very large numbers, which can cause round-off errors. We can get around some of the problems associated with calculating an inverse with a very special type of matrix called an upper triangular matrix. In this type of matrix, the elements below the main diagonal are all 0. If the matrix of coefficients A in the equations governing your system has this form, it's pretty easy to solve the equations using an approach called back substitution. To do back substitution, we just solve the equations sequentially starting with the last row. This row says A44 times x4 is equal to B4. I can solve that directly for x4. x4 is equal to B4 over A44. Now we have a number for x4 that we can plug in here. So we work up to the next equation, which is A33 times x3 plus A34 times x4 is equal to B3. This number goes here, and we can very easily solve for x3. We just proceed backwards through the matrix this way to get all of our unknown values. There are a variety of ways to rewrite a matrix so that it's in upper triangular form. One approach to doing this is called Gaussian elimination. Gaussian elimination relies on the fact that linear combinations of rows of a matrix don't change the information contained in the matrix. I'll illustrate Gaussian elimination in the context of this example. The first thing I'll do is place a 0 at this point in the array. I can do that by dividing 3 by 2, this element by this element, multiplying it by this row, and then subtracting that from this row. That will create a 0 at this point. I do the same thing for the first element in this row. So 4 divided by 2 times this row, subtracted from this row, places a 0 there. Now I want to get rid of this -4 and replace it with a 0. I do the same process between this row and this row. So -4 over -5/2 times this row, subtracted from this row, puts a 0 here. Now the matrix is upper triangular, and I can use back substitution to solve for x1, x2, and x3. Finally, I'll make a few general comments about matrix reduction and elimination approaches. The Gaussian elimination approach that I showed you is not particularly efficient in most cases. There are a lot of other approaches towards reducing or decomposing matrices. Some of them can be more efficient than others, depending on the structure of the matrix they're applied to. MATLAB's backslash operator is very sophisticated. It examines the structure of the operand matrices and tries to choose the best approach for performing the operation based on that structure. MATLAB has a variety of other commands for matrix decomposition. A few of them are RREF, which stands for Reduced Row Echelon Form, LU, which is a lower upper decomposition, ILU, which is a variation on LU decomposition, and QR decomposition. MATLAB's backslash operator has access to all of these approaches to select from when it solves a system of equations. To check the results of my Gaussian elimination, I'll first use MATLAB to solve the original set of equations. A equals 2, 1, -1, semicolon, 3, -1, 2, semicolon, 4, -2, 1. And B equals 1, semicolon, 2, semicolon, -1. I'll use the backslash operator to solve the equations. So this is my solution from the original equations. To check this result against my Gaussian elimination results, I'll first use the last equation in the upper triangular version of the equations. That equation is -13 over 5 times x3 equals -19 over 5. So x3 is equal to -19 over 5 divided by -13 over 5. That agrees with the x3 I got from the original equations. I could go ahead and use back substitution to find x1 and x2, but I think I'll just solve the reduced system of equations using the backslash operator. I'll set a underscore upper equals 2, 1, -1, semicolon, 0, -5 over 2, 7 over 2, semicolon, 0, 0, -13 over 5. And b underscore upper equals 1, semicolon, 1/2, semicolon, -19 over 5. To solve these, I'll type x underscore upper is equal to a underscore upper backslash b underscore upper. This solution is the same as I got from the original equations, so both forms of the system of equations are equivalent. In the next chapter, I'll talk about curve fitting, or how to estimate a line that best represents a set of measured data. One approach to curve fitting is to solve a set of overdetermined equations in which there are more equations than unknowns. The techniques for solving those equations are similar to those of this chapter.